So with functions, what you have to understand is a lot of teachers in the past might have talked about something called a function, but really it was a relation. And functions have very specific definitions. So if you want to have a function, you have to have some kind of relationship that has exactly one output for every input. And oftentimes a good way to see this is with a picture. So I'm not going to draw a picture for every single thing that we have up here. But if you were to draw a picture, that would maybe be helpful. For example, in this first problem that we have, is this relationship a function or not? I could draw a graph and put these points on. So like for a -2, I'd have 3. And you don't have to graph this, just to show you visually what's going on though. And then at -1, I would have a 3 and a 4. And if you remember anything about algebra from way back when, you know that this thing right here fails the vertical line test, and which means no, it's not a function. Because if you can draw a vertical line and hit more than one point, it's not a function. And what you'll notice is that there is one x value going to 2 y values. So if an x goes to more than one y value, something is not a function. If an x value goes to more than one y value, it's not a function. B and C, instead of drawing arrows, decide to use ordered pairs. No big deal. Again, if you wanted to, you could draw a picture. But what I want you to notice is that if you look at the x values only occur one time each. So the 2 only goes to a number, the 3 goes to a number, the 4 goes to a number, the 5 goes to a number. The 2 doesn't go to 2 different values, it only goes to one value. So the answer to this particular problem is yes, this is a function, because there isn't an x value that goes to 2 y values. Whereas if you look in the next one, down below, you'll notice that there are 2 different 2's, which means that if I look at the x value of 2, it's going to both the number 1 and the number 3. So for the x value of 2, there are 2 y values, which means letter C is not a function. And then in letter D, instead of writing them as a chart with arrows or ordered pairs, they put it in a table. And we need to recall, of course, then that in a table, the input is my x value and the output is my y value. So as I look at the x values, I notice that there are a lot of things going on here. For example, there are 2 x values of 0, which indicates that the x is going to more than one y value. In addition to that, there are also x values of 1 that are going to more than one y value. So for sure, this table is depicting a relationship that is not a function. And the big idea is if an x value goes to more than one y value, not a function. Questions about any of those examples? 3 different ways to depict them: chart, table, set of ordered pairs. All right, hearing none, let's move on. In number 2, they talk about whether an equation is a function or not. And really what you need to know is if you know what a picture of this graph looks like, you're going to know already what's going on. So, for example, letter B is a line. If you solve for y, all lines, unless they're vertical lines, are functions. So you can just say yes right away. In the second part, if you look at this graph, this is a sideways parabola. We'll learn more about that later in this class, a very detailed version of what's going on. But whenever you see y squared, it is a parabola that opens up either to the left or to the right. So the answer to this one is no. And the key is whenever you see a y squared, that happens. Drew.
Was that the table on the last page? Sideways.
I don't know. I didn't graph it. It is definitely possible. Could be some points from that. That's a good observation. I didn't really take a look at see what the graph would have been. If you were actually to do some algebra to see why this is true, if I solve for the y over here, I would have y squared equals 4 minus x. And then to get to y alone, I would need to square root both sides. And we talked about in our class, whenever you square root a variable, you have to go plus or minus. So I would really have y equals plus or minus the square root of 4 minus x. And what this is saying is that there are actually two equations. There's a y equals 4 minus the square root of x under a radical, and there's a y equals the opposite of 4 minus x under a radical. What that means is that there are two y values, plus 1 and a minus 1, and that's how we know it's not a function. But the big thing is really, if you ever see y squared, not a function. If you ever see y squared, I knew you just wrote that down, it's not a function. Now in math, people like to be very descriptive. They like to be very prescribed. They like to have a rule that can work for anything. So we've talked about something called independent and dependent variables. We do what most people would consider at higher levels of math, very simple math. And as you get farther and farther along, you have to be more descriptive. So now instead of just saying y equals something, they're going to go with f of x. F of x really means the same exact thing as y, but the f of x tells you a little bit more. It's more descriptive. It tells you that the x thing is your independent variable. That's what it's telling you. But if you want to think about it in its simplest form, f of x means y. So whenever you see f of x, g of x, h of x, j of x, anything that has a letter with a parentheses, the stuff that goes in the parentheses is being put into the independent variable. For example, in letter A where I see g of 0, what this means is that I'm going to have 7 minus 3 times 0. I look back up to the g function, and into that function, wherever I see the x, I plug in what they gave me in the parentheses. That's what it's telling me to do. So then, if I simplify that, I get 7. In letter B, same idea. I look back up into the g function, and wherever I see an x, I put in 7/3. So g of 7/3 means 7 minus 3 times 7/3. If I simplify that, I get 7 minus 7, because the 3's reduce, which gives me 0. In the last one, what's weird about that last one?
There's an unknown variable.
There's another variable. It's kind of weird. They're putting a variable in for a variable. Have no fear, no big deal. Same idea. I look into that highlighted blue equation, and everywhere I saw an x, I put it s plus 2. So now this becomes 7 minus 3 times s plus 2. This, of course, means I have to use the distributive property. So now that's going to be equal to 7 minus 3s minus 6, because the negative 3 got multiplied by the s and the 2, which then turns out to be, in simplified format, 1 minus 3s. Joe? Oh. Questions? Basically, when you see something in parentheses, plug in. Sarah.
Wait, so we're just, like, this says equals to, but what, like, would you say G is equal to standard for A, or? what?
They already wrote down the G whatever, so you don't have to write it down every time.
But technically it would be.
Technically, it's G of s plus 2 equals 1 minus 3s.
Oh.
Anybody else? As Jim Carrey would say, alrighty then. Piecewise function. The first thing I want you to know is whenever you see some kind of function notation with a brace, that's going to be what they call a piecewise function. Piecewise means I have more than one part to my function. And the way this works is there's a condition put on. So at the end of this stuff, you'll see these x less than equal to 1 or x greater than 1 conditions. Those are conditions. So for example, Gannon wants to go out tonight, hang out with his friends, and I say, you can go out tonight and hang out with your friends if you wash the dishes. So Gannon washes the dishes, he gets to go out with his friends. Gannon doesn't wash the dishes, he does not get to go out with his friends. Doing the dishes is the condition. In this case, the 1 is the condition. Look to see what's going on, and that tells you what to do. If I look at f of negative 2 in letter A, the negative 2 is a number that is less than or equal to 1. That means that I am using the green stuff. So I look in the green stuff and I don't use the 1 stuff at all. I just look inside of here and I plug it into the equation part that goes with that condition. So that's the x squared plus 2 stuff. So I have something squared plus 2. This is the actual function. The green highlight was the condition. What number goes in?
Negative 2.
Negative 2. So I shove in a negative 2 because it told me that's what I was supposed to do. And then I simplify it. Negative 2 squared is 4 plus 2 more, and my answer is 6. And all that green highlighted thing was telling you is, do I use the top part or do I use the bottom part? That's it. Nothing more. Because there was a negative 2, it told me use the top part. Oh, the next one, letter B, is a 1. Should I use the green stuff or the yellow stuff?
Green.
Green, because 1 is equal to 1. So I'm going to use the green stuff again. This time, when I write down my parentheses squared plus 2, I'm going to dump in a 1, because it said plug in a 1. So 1 squared is 1 plus 2 more, for a grand total of 3. Again, the highlights are only telling you which one to use, top or bottom. They're conditions. That's all they're for. They do nothing else. Last one, f of 2, is a number that's more than 1.
Yes.
So I'm going to use the second part of my piecewise function, which tells me I'm going to write 2 times something squared plus 2. That parentheses is representing the variable x. And into this space, I'm going to dump in a 2. It says dump in a 2. So 2 squared is 4. And I add 2 more after I multiply by 2. And that gives me 8 plus 2, or in other words,